Hello everyone, and welcome back to ARN-engineering. Today I would like to discuss solving a system of linear equations. Now I do want to mention that it is highly recommended to watch the previous video on solving linear equations before this one to avoid any confusion. Now before we start, it is important to know that a system of linear equations can only be solved when the number of equations is equal to the number of variables. For example, if we look at the equation x plus 3 equals to 4, we obviously only have one equation and we only have one unknown, which is x. So therefore the number of equations is equal to the number of unknowns or variables, which means that this equation can be solved. However, if we look at y plus x equals to 3, over here we can see again we only have one equation, but we have two unknowns, which means that for us to be able to solve this equation, we need another equation with the same set of unknowns, being x and y. Now, as I discussed previously in our previous video, when we're solving a single linear equation, our objective is to find the x-intercepts, or at what x-coordinates the linear line represented by a linear equation intercepts the x-axis. However, when we're solving a system of linear equations, the objective is to find at what point, at what xy coordinate, those linear lines intercept each other. So before I start explaining how to solve a system of linear equations, let's try and understand exactly what it means to solve a set of linear equations. So over here we have two equations, y equals x minus 2 and y equals minus x plus 1. So, and as you can see, we have two variables, and therefore the number of equations is equal to the number of variables, and therefore this system of linear equations can be solved. In order to understand this further, let's try and graph these two lines. So we can assign three values of -1, 0, and 1 to x for both of the equations. Let's look at equation number 1, or the first equation for now. So when we assign a value of -1 to x, we get a value of -3 for y. When we assign a value of 0 to x, we get a value of -2 for y. And when we assign a value of 1 to x, we get a value of -1 for y. Now these points can be easily plotted onto the graph, and we can do the same for the second line for values of -1, 0, and 1 for x, and we will get values of 2, 1, and 0 for y respectively, and these can also be plotted onto the graph. Now, as we know, linear equations represent linear lines, and therefore we can connect these lines and show our linear lines. Now let's further extend these lines, and as we can see, when we extend these lines do intercept each other at some coordinate indicated here. Now the coordinates of that point, or the x and y values of that point, is the solution to this system of linear equations. Now, as you can see, we can draw some perpendicular lines to the axis and find approximate values of the x and y coordinates. But let's go through the typical method of solving these linear equations and get proper values for x and y. So, in order to solve a set of linear equations, we need to add the equations together. So if we add these two equations together, we can see that the x terms clearly cancel out, and we will be left with 2y equals to -1. We can easily solve this linear equation and find the value of y being -0.5. Now if we substitute y value of negative 0.5 in one of the equations, in this case I've chosen the first equation, we can rearrange that and find the corresponding value for x being 1.5. Now let's look at the graph again, and as you can see, a x value of 1.5 and a y value of negative 0.5 makes sense, and they do represent the coordinates of our of the point at which the lines intercept each other. Now let's look at another example. Now the main difference between this example and the previous example is that in the previous example we could easily cancel one of the variables out and therefore be left with only one variable, which will result in a simple linear equation. However, in this case we don't have that opportunity. And therefore, usually the first step to solving a system of linear equations is to get to that stage where we can cancel out one variable. So if you look at this, the first equation, we have two ways of achieving that stage. If you multiply the first equation by a negative 4, we will get minus 4x plus 8y being equal to negative 8. Now, as you can see in this case, the y variables can be cancelled out. We could also multiply the top equation, the first equation, by negative 3. And that will give us negative 3x plus 6y equals to negative 6. And in this case, the x terms can cancel out. So let's do both of them and see if we can get the same solution to this system of linear equations. Let's look at the first case first. So as we discussed before, in this case, if we add the equations together, the y terms will cancel out and we'll be left with minus x being equal to minus 7, which will give us a x value of 7. Now if we substitute an x value of 7 back into one of the equations, in this case I've picked the second equation, we will get a y value of 20 over 8, which is equal to 2.5. So let's remember, we got an x value of 7 and y value of 2.5. So now let's solve this system of equations using our second strategy. Now in this strategy we have our first equation being minus 3x plus 6y equals to minus 6, which means that if we add these two equations together, the x terms do cancel out. And we'll be left with minus 2y equals to minus 5, which will give us a y value of 2.5. And now we can substitute the y value of 2.5 back into one of the equations. Again, I've selected the second one. And as we can see, we'll get 3x minus 8 times 2.5, which is 20, being equal to 1. And if we rearrange the equation, we get an x value of 21 over 3, which is equal to 7. So as we can see, this solution is consistent with the previous one, which means that it doesn't matter what value we choose to achieve this stage where we can cancel out a variable, as long as we do reach this stage. Now, so as we discussed before, if the number of equations is equal to the number of variables, we should be able to solve that system of equations. So if we have 3 variables and we also have 3 equations, we should be able to solve that system of equations. However, solving a system of equations with 3 equations and 3 variables in it is a bit different. And the way I go about it is to consider 2 of the equations out of 3 equations at a time. So I group the 3 equations into 2 groups of 2 equations, and I consider each one at a time. And for each one, I eliminate one of the variables and I calculate an equation that yields out of that. And then by substituting those solutions back into those equations, we will be able to find the solution to the overall system of equations. So let's go through this example so it makes more sense. So as I discussed before, we first group them into two groups of two equations. So I've grouped them into equation 1 and equation 2 being in one group, and equation 2 and equation 3 being in another group. Let's rewrite those systems of equations. And let's start by adding each one of these groups, the equations within each group together. If we add the first group of equations, we can see that their x terms cancel out, and we'll be left with a single equation of y plus 3z equals to 11. Let's do the same thing for the second set of equations, and again, as you can see, the x terms do cancel out, and we're left with minus y minus 2z being equal to minus 8. Now, if we look at these two equations, we can see we have two equations and we have two variables, and therefore these can be a system of linear equations that can be solved. So now we are familiar with solving two equations with two variables, and therefore we'll go through the process of adding these two equations. The y term cancels out, and if we look at the rest of the equation, we can clearly see that this will give us the z value being 3. Now we can substitute the z value of 3 back into one of the two equations. I've picked the first one, and that gives us a y value of 2. Once we reach a stage where we've calculated 2 of the 3 variables, we can then go back and use one of the original equations. In this case, I've chosen the first equation to calculate the last variable. For us, that's x. So in this case, we have 2x plus 4 times 2, which is our y, plus 2 times 3, which is our z, being equal to 16. And if we solve this simple linear equation, we'll get an x value of 1. So we've gone through solving a system of linear equations that consists of 2 equations with 2 variables, as well as 3 equations with 3 variables. I really hope this video was useful for you. If you like this video, please support the channel by leaving a like and subscribing to the channel. And thank you very much for watching.